Okay, so hello everybody, and thanks for coming to the second session on machine learning. This is a follow-up on what Nikhil did yesterday, and we will talk in a bit more detail about how we select the model and how we validate its performance. So just for the setup, if you have followed the setup instructions on the main website, or if you were able to follow Nikhil's lecture, you don't need to do anything else. That should be fine. You can just pull the repository to update it. Otherwise, you need to clone the repository containing the materials for this course. And this is the one that's linked in the main website. And then install Python, and there's a requirements file in the exercises folder in that repository. So this is the repository for the course. This is what you did with Nikhil, and now we're in here, and you have some instructions. The slides are here, and we will be doing some of the exercises that are in this exercises folder. I will be looking at some Python scripts. If you prefer to work with Jupyter notebooks, they are here in this directory. You can open them locally, or Isil was kind enough to upload the notebooks to a Google Drive, and you have the link in the repository as well, or on this slide, so that you can open them in Google Colab if you prefer to use that. Do we need some time for setup, or can I just continue?
Yeah, no questions online either, so go for it.
Great. Okay, so I'll start with just a quick recap of what you saw in the first lecture. So you talked about supervised learning, and Nikhil described two broad categories that are regression, when we are trying to predict a continuous outcome. So, for example, the weight, the age, or something like that. And that can be done, for example, with least squares linear regression. And classification, when we are trying to predict a discrete target, so some categories. For example, a diagnosis, whether someone has a disease or not, and this can be done with logistic regression. Then he talked also a little bit about regularization to prevent overfitting, fitting too well the training data, but then failing to generalize to new examples. And we'll be talking a lot about that, and in particular about the simple L2, also known as ridge regularization, which is just putting some L2 penalty on the coefficients of a model. And then the main topic of today's session is how do we choose the best model if we have several options. Nikhil described many kinds of models and their hyperparameters, so we want to choose the best one for our problem, and how to validate it, how to evaluate how well it performs, how good will be its predictions on out-of-sample examples, because again, we never care about performance on the samples for which we already have some answers. So we don't care about, for example, the diagnosis of participants in our training data set. What we want is predictions on out-of-sample examples. So those we have not seen yet when we design our machine learning models. For example, patients that will come to a hospital and whose data was not available when we were setting up our machine learning system. And in order to evaluate that performance, depending on the kind of problem and what is meaningful for our application domain, there are different metrics that we can use. and simple ones are the mean squared error, so the squared distance between our prediction and the ground truth in a regression setting, or in a classification setting, the accuracy, the proportion of examples for which we get for the right answer. And then Nikhil also talked about cross-validation, which is a way to get an estimation of how our model is likely to perform on new examples by splitting our data set and training on part of the data and then evaluating the model on the left-out data, also called the test data. Just to remind us of the vocabulary and the notations. So today we will talk almost exclusively about supervised learning when we have some labels that we want to predict. So we have some target Y, for example, a diagnosis, an age, anything we're interested in predicting. Then we have some features X that are descriptors of our samples. They are our inputs, so they can be all the voxels in an image or some biological measurements and so on. And we model Y as some function of X plus some unmodeled noise, plus some error. And our goal is to approximate that function that maps the inputs, the features X, to the target Y that we are trying to predict. In the simple example of linear regression, Y is some continuous output, and we model it as a linear function of X, so some constant, an intercept, plus a linear combination of the entries in X. So each sample, for example, each patient is described by a vector, say all the voxels in an image, and we build a linear combination of all of these values plus the intercept, and that is our prediction. And we want it to be as close as possible to the target we are trying to predict. So learning, in that case, simply amounts to setting these coefficients of our model, the intercept and the coefficients of the linear mixture of the features that produce our prediction. Is that clear for everybody? I think after Nikhil's lecture, this has been covered. And then the question is, how do we do this? How do we learn? How do we choose the best possible values for, in this case, beta 0 and all the beta j? We do it by empirical risk minimization. So we choose a function that tells us how bad is our error. For example, the squared distance between our prediction and the true value that we are trying to approximate. So this should be tailored to our application and what kind of measurement of the error is meaningful for our setting. And once we have chosen this loss function, we are interested in making it as small as possible in expectation on some new example. So we want the expected, for example, the expected squared error on some new patients for whom we will make a prediction to be as small as possible. But of course, that's an expectation, so we are not able to compute it exactly, and even less to minimize it. So when we are interested in a mean that we do not know, and we want to estimate it, what we usually do is we collect a sample from the population, and we compute an empirical average. So that's what we are doing. We will replace the risk, which is the expected error on a new patient, with an empirical risk, which is the average on a sample of patients that we have collected and that constitute our training data. So we gather n training examples for whom we have both the features, say the image, and the target, for example, the age or the glucose concentration, or whatever we are trying to predict. And we minimize the empirical risk, which is the average loss on these training examples. So in the example of linear regression, where we want to minimize the squared error, we are trying to minimize the sum of squared errors, so the sum of the squares of the differences between the ground truth and our prediction, which is here, on all of these samples. And when we have found the parameters that minimize this empirical risk, we have fitted our model to our training data. So we always want to do two different things. What I have just described, which is setting the parameters, building our model, and then we want to know how well it will perform. Before we start using it, we want to know if it has any chance of being useful or making good prediction, or if it's going to be terribly wrong all the time. And we can never do both of these things on the same data. I cannot use the same participants, the same sample to choose something and also to evaluate the quality of my choice. So if you remember only one thing from today's session, it's really this, that we cannot make a choice and evaluate that choice on the same data, because if we did, that evaluation would be biased, would be optimistic. And try to illustrate that. And then we will talk about ways to avoid doing that and mistakes that are easy to make and that could lead us to falling into that problem. So just to illustrate that, a very simple example. As you know, the World Cup is ongoing. And every time this happens, there are some animals that make predictions about the outcomes of the game. So, for example, someone shows to a dog or something 2 flags of the 2 teams that are going to play, and the first one it touches is the team that is supposed to win. If you look it up, you can find tons of videos about that. And suppose that we have had 30 different animals making these predictions like this for all 16 games of the knockout stage of the previous World Cup that happened in 2018. So here are their average accuracies, so the proportion of matches that they got right during the 2018 World Cup. And we will select the best of them. So this octopus here got an accuracy of 0.8, so it seems very good. And now we will want to use it in this year's World Cup. So we ask him to make predictions on the 2022 matches, and we hope that it will perform very well, because it was performing very well in 2019. So a quick question. This octopus in this year's World Cup, do we expect it to perform better than in 2018, so have a better accuracy, a worse accuracy, or on average in expectation the same kind of performance as last time? And I will ask, so everybody who thinks it will perform better, please raise your hand. Now, who thinks that it will perform worse? And who thinks it will be the same? And now, Nikhil, can you tell me roughly what people prefer?
So there were 0 people.
Just enable the video.
Hello?
Yes, we're trying to enable the video. Yeah, again, so I think there were 0 people who said it will get better. I think most of them said it will get worse. I think there was 1 or 2 people who said it will be the same.
Okay, thank you. So that's great. Indeed, it will be worse, because here in 2018, we have selected the best of all these candidates. So by construction, because of the way we selected it, it's going to have a good performance, because in order to be selected, most likely it performed exceptionally well on this data set. So in order to get a good evaluation of its prediction, of its accuracy, in order to get an unbiased estimator. Once we have selected it, we need to reevaluate it on some new data. So, for example, on a new set of matches. So the performance on the data that was used to select the predictor is a biased estimator of its expected performance on new data. Again, because the 2018 World Cup was used to choose that octopus, its performance then is a biased optimistic estimator of the expected performance in future World Cups. That was just an example, but if I repeat the same experiment several times and then plot the distribution of the performance of the best here and then its performance in the new data set, we see that these distributions are different. And that systematic difference here between an estimator and the true value that we're trying to estimate is called a bias. So that's why we cannot use the training error to estimate the model performance, because this was with 30 animals. But if instead we have an infinite family of machine learning models indexed by some parameters like the beta 0 and beta we were talking about, the same principle applies. We cannot use the training data set to select our model, to select the parameters, and then again to evaluate it. So we need to choose the model, the predictor on training data, discard its performance on that data, and evaluate it again on some test data, on some new data that wasn't used to choose the model or its parameters. So whenever you hear that a selection is taking place, we pick the best, we select something, think that the performance that was used to select it is a biased estimate of what we are really interested in, which is performance on new data. So we need to bring in some test data. I hope that's clear for everybody. And now we will start looking at how to do this kind of supervised prediction with scikit-learn, and then how to do the evaluation on testing data. So as you know, after Nikki's lecture, scikit-learn, it's a Python package for machine learning. And we will use only a very small subset of it today. But what's important is to understand the main API, application programming interface, so the set of methods that the scikit-learn estimators expose and that we can use, because once we have understood this, it's easy to use any of the simple or elaborate methods that are implemented in scikit-learn, because they all offer us the same simple interface. So how it works is we have an estimator, for example, in this case, one that implements the ridge regression. We initialize it possibly with some hyperparameters, and then we call its fit method so that it can learn the best parameters on some training data. So we pass the features, the inputs, and the targets that we want it to be able to predict, and we fit it like this. And then when we want to obtain some predictions, again, remember that we are interested in prediction on some test left-out data, so there's no overlap between this data here and the training examples. We call the predict method and obtain our predictions. And if you have downloaded the slides here, you have links to the scikit-learn user guide, in which you have lots of great explanations, and to the documentation for that specific model. And once we have our predictions, we want to know how good they are. So scikit-learn has a metrics module that implements all kinds of performance metrics that might be relevant for our problem to estimate how good our model is doing, how good are our predictions. In this, if we are doing linear regression, if we are doing regression, again, the mean squared error that we already talked about can be a reasonable choice. So it's also implemented in this metrics, and we call it with the ground truth, and then our predictions, and it outputs a score. So just to warm up, we will try to do this on a simple example.
Jérôme, your video and sound just went away. I'm not sure if you can hear us. Sorry? Yes, the first exercise, yeah.
Try to work on that while we're.
So I've sent him a request to join again.
Okay.
I've asked JP to tell him that he needs to accept.
Yes. All right, he's back.
You can actually
Try again. Can you hear us?
Is it okay now?
Yeah, we can hear you now, yeah.
Okay.
You'll have to go back to the example that you started with.
Okay, so where did I stop? Was it here?
Yeah, so I think you're going to the actual Python code. So that's good.
Okay, so again, it's in that folder with all the exercises, and it's exercise 1. So please start by opening the one that's called questions and not solutions. Is everybody ready to look at it?
Is everybody on the first exercise? Anybody has trouble finding how to get there?
They were doing an exercise folder, that exercise folder.
I shared the Discord, this one, and the chat folders, and the first exercise there. Click on it.
So just raise your hand and I'll show it to you on your laptop. Okay. Is everybody okay on Discord or Crowdcast? Oh, I'm not on. Yeah. Yeah, people on Crowdcast or Discord just put a message here, and because we are monitoring the chat, so if something, if there's an issue, just let us know.
Okay. Were there any questions about what I talked about already? Okay. So in that first example, we just import NumPy that you are probably familiar with, and then the ridge model I just talked about from scikit-learn, and the mean squared error, and this function that we will use to generate some fake data, because here we don't really care about any particular data set. we're just trying to illustrate how cross-validation works. So in all of these examples, we will use that utility function from scikit-learn that is used to simulate some fake data. So some simulated X and Y with sort of a linear relationship plus some noise. And we choose here to put 80 samples and 600 features. So X has 80 rows and 600 columns. And then some noise, and the random state is just we set it so that we don't so that we get the same data every time. And this random state, it's a thing that most of the functions or estimators in scikit-learn that use some randomness, some random numbers, you can set that so that the output you get from your scripts is actually deterministic, and you get the same result every time. And then we initialize the model as we did. Here we give it a value for its hyperparameter alpha. You don't really need to care about it now because we'll talk about it later. We choose a small value, so that model is actually very close to an ordinary least squares regression. And then, as I showed in the slide, we fit it to the features and the labels. And then we use the predict method to obtain some predictions. And then we use this mean squared error from the metrics module in scikit-learn to obtain the mean squared error that we can print. So can somebody tell me what is the issue with the code that I'm showing here? Nikhil, can you still hear me? Yeah.
Does anybody have a? He can't see them anyways. No, because he's sharing his screen. Yeah. Yes.
We're not splitting the data.
Yeah. So my answer was we are not splitting train and test data.
Okay, exactly. Yeah. So you can still hear me and see my screen? Everything is working
Yes.
okay now?
Yes.
Okay. So you are right. That's the problem. Here we use some different data for fitting and predicting, and here we are using the same X that we use to fit the model in order to get some predictions, and the same Y to evaluate the prediction. So if we look at the mean squared error, because we have more features than samples, in that case, our linear model is able to fit perfectly the training data. So here, this will print 0, and yeah. Okay, so here, when we evaluate the model's error on the training data, we get a perfect prediction because it has more parameters than we have equations. So the problem is imposed. It can fit perfectly these 80 samples, and we get we get 0 error on these training samples. That doesn't actually tell us that it will perform well on some test data. So now we're actually we're interested in the testing performance, the performance on unseen data. So I generate the data in the same way, but this time instead of 80 samples, I generate double the number, 160, and I split it. I put the first 80 in the training dataset and the remaining in a testing dataset. I initialize the model as I did before, and now I will give you 5 minutes to fit the model on the training data, test it on the testing data, and then tell me if you are seeing a similar performance as on the training data, or if it's very different.
is everybody clear on what to do?
So it's very easy. It's just a question of basically redoing the same thing as here. It's just the first simple exercise to get us set up and make sure everything is working properly.
Does anybody have an answer for the test? Let me see it.
Yeah. It's 25,000.
Okay, we have one answer, 25,000. Anybody else? Same.
Okay,
You're saying
I'm also
25,000. Yeah.
I'm also getting the same. So as you can see, the training error was 0. It seemed that it was working perfectly, but when we correctly evaluate our model on some testing data, we see that the error is huge, and actually it overfitted the training data, and it doesn't work at all. So yeah, that's. So here we use the mean squared error to estimate our prediction, which is just the average of the squared differences between the ground truth and our prediction. But there are many other metrics that we can find in the scikit-learn metrics module that might be more informative. For example, Nikhil told you yesterday that in the case of classification, the accuracy was not always meaningful, in particular when we had imbalanced classes. Here we are looking at regression. Some useful metrics that you can use are the R2 score. So this one, we also compute the sum of squared differences, and we divide it by the, we can compute the average squared difference and divide it by the variance of the data. So here, y with that bar is the mean of the labels in the training data. And we compute the sum of squares between the training examples and their mean. And then we take 1 minus this quantity. So if we have perfect predictions, every time our prediction y with a hat is equal to the true value, the difference is 0. So our R2 score is equal to 1. If we found the mean correctly, but we don't explain any variance, we haven't fitted the data at all beyond just learning the average. This means that here we are predicting y bar, the mean, every time. So that is if we are able to predict approximately the mean of the testing data. And these two quantities are the same. So in that case, if we're just predicting the mean, we get 1 minus 1, and R2 score is 0. And if we're even worse than that, we get negative R2 scores. So it's also based on this sum of squared errors, but it has an interesting scale because we know that a perfect prediction will give us 1, predicting the mean will give us 0, and negative R2 scores are even worse than 0, are below 0. So it has a nice interpretable scale. Another metric that can be useful for regression is the mean absolute error. Instead of computing the squared differences, we compute their absolute value. And that's helpful because in that case, the average has the same unit as these labels. So when we are trying to predict a quantity that has some meaningful unit, for example, an age in years or a weight in kilograms or something like that, our error can be measured in years or in kilograms rather than in squared kilograms, which makes less sense to us. So that's also a very useful metric. It's much harder to optimize as a loss, but it can be very informative for evaluation. And these are just 3 examples, but there are many more in the scikit-learn documentation for the metrics module. And now, cross-validation. So before, we split the dataset just once into a training set and a testing set, and we train on the training data and tested on the testing data. And when we do cross-validation, we do this several times so that we train and evaluate several models. And that is interesting because if we do it just once, we might get lucky and do a split where the testing examples are very easy, for example, or we just get one number and it doesn't give us a very good idea of how this number would have varied if we had split the data differently. So in cross-validation, we do these splits many times, and this is the probably most popular choice of k-fold cross-validation, where the testing sets never overlap. So in this case, in 5-fold cross-validation, we divide the data into 5 parts, and each time we use 4 of them to train the data in blue, and we evaluate on the remaining parts. And then we choose another part for the test set, and we train on all these blue data and test on the orange data, and so on. And by doing this, we sample a little bit the variance of the models because they have been trained on slightly different training sets, and also the variance of the evaluation because we are testing them on different test examples. And of course, these training sets overlap. So the models that we train are not independent. So the scores that we obtain like this are not independent. So we cannot like estimate their variance or make any statistical claims about the results, like saying we get scores that are significantly above 0.5 or something like that. But still, it gives us a better idea of how the model is likely to generalize when we apply it to some unseen data for which we expect it to actually make useful predictions. There's a lot in the scikit-learn user guide about cross-validation. K-fold is one way of splitting the data, but there are many more schemes. And scikit-learn provides us 2 functions to do this whole thing for us. One is cross-validate, and the other is very similar. It's cross-val-score. It's just a slightly simpler interface to cross-validate. So it does less things and return less results, but it basically does the same thing. And we will use cross-validate in the second exercise. So here it is. We make the regression using the same function to generate some simulated data. And again, we will be using a ridge regression. And now I would like you to look at the scikit-learn documentation for cross-validate. You have the link here or in the slides, and find how to use that function in order to obtain cross-validation scores for our model on this X and Y dataset.
Jérôme, there is a question.
Yeah.
The question, I mean, you can also see it from the crowdcast, which basically says for other people here, if the model would be different in each fold, which model shall we choose for the final version?
Right. That's a very good question, because here the training sets are different. So for each of these folds, we get a new model, and when we evaluate it, we get a new score. So what we are really interested in here is to evaluate our method to figure out if we apply it to some new training data and then evaluate it on some new testing data, how the model is likely to work. So we are evaluating our method. So all we are interested in here are the scores that we can report about our model, and we can discard the models. Or if we are not just interested in evaluating the method, and then we also want a model that we have trained and we can deploy, there are several things that we can do. We can refit one model on the whole data. Most likely it has seen more data, so we hope that it will perform at least as well than these models here, and it should be, if we got good scores here and we are satisfied, retraining the whole model on a model on the whole training data should give good results as well when we eventually apply it to unseen data. Or as we have already fitted 5 models, we can take advantage of that to build an ensemble model. So instead of training one new single model, we keep all of 5, and when we have some test data, we get the 5 predictions and then compute an average, or if we're doing classification, ask them to vote or something like that. So we aggregate the predictions of all 5 models, and sometimes that reduces a bit the variance of the predictions and can give us an even better model. But for example, the simplest thing that is often done is, once I have seen these scores, if I'm happy, then I refit a model here on the whole data, and then I save it, I deploy it, I ship it, I do whatever I want with the model I wanted to train. So were most people able to use that cross-validate function and see some cross-validation scores? Sorry, was there another question?
There's another question. Hold on. I'm assuming you didn't hear the question.
No.
So the question was, what is the point of calculating cross-val score if we are going to find accuracy? But the model accuracy, cross-val score gives you like a distribution of model accuracy, though, right? Like it's not. Yes. The question is the model accuracy an average of the cross-val score?
The true accuracy on some new data, or
so
basically the average of the cross-val scores gives us an estimate of the accuracy.
So yeah, so if you just take one train and test split, right, so you get one model accuracy, but that's just mere. It could be just by chance, bad or good with the split. So by doing the average over the cross-val score, it's basically an aggregation of multiple splits, gives you a better estimate of what model accuracy could be. Is that, do you want to add something to that, or is that?
No, yeah.
Okay.
The score on test data gives us an estimate of the model's accuracy, or in this case, mean squared error, or whatever we want to evaluate. And by
No, the third thing. He said that we talked about it before it did, but right. So what are you doing something on your trends? And we have to invest multiple models to get people, and then you can use that one model on the test set. Predicts. I think he's going to get there in a second.
So I think she's having a question about the nested cross-validation part, which I believe you will get to in the next slides. So there's an internal cross-validation that she's doing, which means you get a cross-val score for just the one of the splits of the train and test. And then using that cross-val score, she's testing the best model on the test set. So you get accuracy on the test set. So I think you're going to go on the nested part of this whole thing. So I'll just wait until you explain that part.
Right. But here we are not setting any, we are using just one default hyperparameter, so we can get that nested cross-validation you're describing. It's usually more for setting a hyperparameter or selecting a model. So in this case, we can here, as our model doesn't have any hyperparameters and we're just trying one, we can use just the plain Crossval score. Do you think we need more time, or can we move on to the solution?
Anybody else has any questions, or should we? Yeah, I think we can move on to the solution.
So here is still the same script, and we have here the call to that cross-validate function. So we use the cross-validate function from the model selection module, and then we give it the model that we are trying to evaluate. So that's this one here. And then the whole data set. So the whole X matrix, all the features, and all of the labels. And the function will take care of us of splitting it into training and testing data and implementing that whole thing. So we give to it all of our data, this whole thing there, and it will split it several times and retrain the model each time and evaluate it and produce the scores for us. So if I run it, we obtain the scores like this, and it actually returns us a dictionary with different kinds of information. And if we print them here, the one we are interested in now is this test score, where as we did a 5-fold cross-validation, we get 5 scores for each of these evaluations. And we also get how long it took to fit and so on for each of these folds. And these 3 parameters are the only ones that are required. And then we have some optional parameters that I chose to use here. The scoring method, where we tell it which metric it should compute, because here you can see in the test score, it's giving me some values. I can decide if it should use the mean squared error or the absolute error and so on that I talked about. And it has a convention that it should be a score. So higher must mean a better model. So here, instead of the mean squared error, we use the negative mean squared error, because then the negative mean squared error means a higher negative mean squared error is a lower mean squared error, and the lower mean squared error is a better model. And then the cross-validation parameter is how we want to set up the cross-validation. So here I tell it to use the k-fold cross-validation, which is this organization here, with 5-fold, but I could choose something else as well. And it will make reasonable default choices for me if I don't specify these parameters. But because there are so many kinds of models and problems and so on, the default choice is not completely obvious. So sometimes you really have to dive a bit deep in the documentation to figure out what it will use by default. Because in some of these cases, the default is none or auto or something like that. And the documentation says if it's none, it will make a good default choice, and that's true. But if you want to be sure of what it uses, you can either explicitly set the parameter yourself, or read a lot the documentation, or step through the code in a debugger to see exactly what is going on. And that's also very informative to do, because the default choices that are made by scikit-learn are usually good choices, so that can also tell you about what is a good idea to apply when. If in this case, if I hadn't set these parameters, by default, because it is a regression problem, it will use the R2 score that I talked about before. And then the k-fold validation is also the default choice for a regression problem. If it was classification, most likely it would use the accuracy, and it will also do a k-fold cross-validation, but for classification, it's when it does the splits here, by default, it will try to make sure to keep the proportion of each class about the same in all of the test sets. And then I call this function, and I get my scores. If I think that this is a good mean squared error, again, maybe the mean squared error, it's not very easy to interpret, so I can run it again with the default choice to get the R2 score instead. And if I decide that this is good for me, then, as we discussed, I can refit a model on the whole data, or build an ensemble model by averaging them, and save my model to reuse it later or deploy it for my application. Are there any questions about this exercise? Okay. So now we will talk about model and hyperparameter selection, because as you saw, we have been using a ridge regression model that is has a least squares penalty. It's like a linear regression, but we add an L2 penalty on its coefficients. We shrink the coefficients towards 0 to constrain the model and prevent overfitting. So I'll just explain how, repeat why we need to do this, and then explain how we can select the amount of penalization, the amount of regularization that we apply to it. So we just have to remember that when we do linear regression, we have our targets Y here that we should learn to predict, and our features X. So each row corresponds to a sample, and each of these columns correspond to a different feature in X, for example, a different voxel in the images, a different voxel index. When we fit a linear regression, what we are really doing is learning these coefficients beta that I showed before and that Nikhil also talked about, that produce a combination of the columns in X that approximates well the labels Y. So we want to build our prediction or approximation Y hat as a linear mixture of the columns on X that is as close as possible to Y. But if we have many features in X, which is very often the case in the settings we are interested in, for example, if we have one feature for each voxel in an image, or for each gene or something like that, we have a huge number of coefficients to set here. And if we have more features than samples, we have many different ways of setting the coefficients in a way that results in a perfect reconstruction of y, because we have a linear system of equations with more variables than equations. So we have many solutions, and the variance in these coefficients is huge. We have an infinite space of solutions. So we are unlikely to select a good value for beta, and we will get a perfect reconstruction of y on the training data, but on unseen data, our model will not work at all. As we have seen in the first exercise, we get 0 error on the training data, but catastrophic predictions on the test data. So we need to somehow reduce the number of parameters or constrain the model to make it well posed. So two broad categories of solutions can be regularization, that we'll talk about now, putting some penalty or some constraints on these coefficients to reduce their variance, or dimensionality reduction, so reducing the number of columns in X that we will talk about later. So the simplest kind of regularization we can use in this case is the ridge regression that we already talked about. We add a penalty on the size of these coefficients. So we still have the same X and have to learn the same coefficients, but we say that they should stay close to 0, because otherwise we can have, if we have columns in X that are not linearly independent, we can have some coefficients becoming huge while others become very small, and they cancel out. And like this, we can have a very crazy coefficients that can take very large values because they cancel each other out. So to prevent this, we can shrink these coefficients towards 0 and say that the model has to pay a price in order to select coefficients that have a very large norm. The loss is still the same. We are still minimizing the squared error between the true value y and our prediction, which is the intercept plus the linear mixture of the columns in X. But we also pay a penalty for selecting large coefficients. And the amount of shrinkage we apply, the intensity of the regularization, is controlled by this hyperparameter alpha. So it's a hyperparameter, not a parameter, because it's something we select before fitting the model. It's not something that's adjusted to the data, but before fitting the model, we set alpha, and then we minimize this quantity. So that's something that we have to choose somehow, and we will talk about that. Sorry. So here I'm fitting this ridge regression model on some example data. I don't know if you can move that. No. So I generate some simulated data and fit a ridge regression model, and then I look at the R2 score on the training set. So remember that R2 equals to 1 means perfect prediction, and the R2 score on the test set. So here R2 equals 0 means a prediction that is no better than just predicting the mean. And I do this several times, and I average the results and show their standard deviation here. So that's why you see here this line is the mean across many simulations, and this is the standard deviation. And I use, as I said, a linear ridge regression. So it has this hyperparameter alpha that I need to set. And I have done the experiment for several values of alpha. So I tried with alpha equals 10 to the minus 2, minus 1, alpha equals 1, and then also very large values of alpha. And I see what kind of training and testing errors I get for these different values of alpha. So on this side, I have a very small alpha. So a small alpha, if I go all the way to alpha equals 0, this term here disappears, which means I am looking only at the loss, at the data fit term. So I'm back to fitting an ordinary least squares linear regression. I'm not putting any regularization at all. Whereas if alpha becomes very large, then this term becomes very important compared to this one. So when I try to minimize this quantity, I end up caring mostly about that. And so if this term wasn't here, of course, the beta that minimizes this second term is 0. So if I choose a gigantic value for alpha, I am pushing all the coefficients towards 0. And in between these two extremes, there's probably a good sweet spot that corresponds to a good hyperparameter that will give me a model that generalizes well. So again, on this side, we are close to ordinary least squares regression. And on this side, we are setting all the coefficients to be almost 0. And here we see how the testing and training performance evolves. So when I put no regularization at all, we're in the problem where the model has too many parameters, not constrained enough. It can do whatever it wants. So it is able to fit perfectly the training data, but it generalizes very poorly. And then as I increase the value of alpha, I add more and more regularization. I am constraining more the coefficients, so the model is less able to fit perfectly the training data. So the training R2 score starts to decrease, but the variance of the coefficients is smaller. I'm choosing a better model. So the testing error, the testing score is actually improving. But then if I go too far, as I said, I'm setting all the coefficients to 0. So I end up just predicting the mean of the training data, because we usually don't put penalty on the intercept. And so my R2 score is getting very close to 0. Here, so these here are the scores. Here I'm showing a few example coefficients. Remember that the prediction is built as a linear combination of the features. So we have several coefficients, beta 1, beta 2, and so on. And as these are simulations, I know the true value of the best model. So the values of these coefficients that I am trying to estimate, because it's simulated data and I set them myself. And I am showing them here with that dashed line. So this is the true value in the model that was used to generate the simulated data. And in green is the estimate that I obtained by fitting the model. And again, that's averaged across several repetitions of the experiment. So when I have a very small alpha, the model is not very regularized, I am letting the model fit perfectly the training data. And on average, the coefficient I estimate will be close to the true value. But because it's an unbiased estimate of that value, so on average, the average across many repetitions of the experiment is close to the true value for the coefficient. But as I said, it has a huge variance because the dimension of the input is too large. The problem is ill-posed. The values of these coefficients can fluctuate a lot. So the mean is close to the true value, but as you can see, the variance is huge, which means that although on average I would get a good estimate, of course I can only fit it to one data set, and so I'm unlikely to land close to that mean, So I get some bad value that can be anywhere around it, and I get a very bad generalization. As I increase the amount of regularization, I am shrinking the coefficients, pushing them towards 0. So I am adding some bias to the coefficients, and I bias them towards 0. So you can see the average estimate that I obtain for that coefficient across repetitions of the simulation, getting pushed away from the true value and towards 0. I'm adding some bias, but because of that regularization, because I constrain it more, I can see also that the width of this light green area is decreasing. So the variance of the coefficient is decreasing. So I'm making a trade-off where the mean is getting more and more wrong. I am adding bias, but the variance is decreasing. So I am getting a better estimate. And we can see that as this happens, the generalization error is improving. The training error, the training score is decreasing because I am adding bias, but the testing score is actually improving because I am reducing the variance of my coefficients. And it's particularly obvious here. Here, the true beta 4 coefficient is actually 0. So the fourth feature, the fourth input, is not informative at all about the label. And we see that on average, my estimate is always 0. But if I don't have any regularization, the variance is huge. Whereas as I add regularization, the variance decreases. So when we have a model with many features, many of which are unlikely to be informative, adding that kind of regularization can be a good way to avoid having wild fluctuations of these garbage noisy coefficients. But as I said, if I go too far, then I am biasing the coefficients too much. I am pushing them to be almost exactly 0. And then, although their variance keeps decreasing, they are just too biased, that they are too far from the truth. And the testing score starts to decrease as well, until eventually I have set all my coefficients to 0. So all I am predicting is just the mean of the training set. So I have like this a kind of a family of models that are indexed by this hyperparameter alpha. And I have to find that sweet spot here, that trade-off between not constraining the model enough and constraining it too much. And on one side, I will have too much variance. On the other side, I will have too much bias. And that's why we call it this bias-variance trade-off, which is a term you already heard in the Nikhil's session. Is that more or less clear for everybody?
Are there any questions so far? This is a bit technical, so if you have questions. Yeah, we're good.
Great. So how do we find that good value for alpha? We can do what I just did now. So we.
Sorry, Jérôme.
Yeah.
Is we going to take a break sometime soon? Is it a good time now or sometime soon? Just let me know.
Sure, now is a good time. Yeah.
It's a good time. All right, we should take a break for like 10 minutes. Yeah, so it's 10:34. We'll be back by 10:40.
If there are no questions, then as I said, how we do choose this rich hyperparameter alpha. And by the way, often in books, you will see it being called lambda, or in papers. In scikit-learn, it's called alpha simply because lambda is a keyword in Python. So we use alpha here as well. It doesn't matter. So as I said, we can try a few values of that alpha, do what we were doing before, like splitting into training and testing or doing cross-validation to evaluate the performance of the model indexed by a specific value of alpha, and then pick the best. But of course, when we pick the best value of alpha, as you know, we need some new data in order to evaluate it. So it's really the same reason that we couldn't evaluate one model on its training data. So remember before we were selecting the parameters beta that gave the best prediction on the training data. And then that training prediction score for the performance of beta was biased. And now it's the same problem for the hyperparameter. If we repeat that cross-validation or that train and test split for several values of alpha, and then select the hyperparameter alpha that gives the best prediction, that score that we use to select it is biased. So we need to bring in some new data, another set of data that we didn't use for the cross-validation for the selection of alpha, and do a new evaluation of just one model with one hyperparameter, the one that we selected. So we end up with several values for the we end up with a more complex cross-validation scheme, because we now have to add a nested loop of cross-validation to be able to select the best alpha. So again, if we were doing just one split, we would now have three data sets, one in which we fit a model for all possible values of alpha, and then a validation set on which we evaluate all of these models. And then on that validation set, we pick the best value for alpha, refit the model corresponding to that value, and then evaluate it on the final test data that was not used to fit any model, nor to select the hyperparameter alpha. So when we do this as a cross-validation, it looks like this. We have an outer loop of cross-validation that corresponds to the loop we had before of train and test. But then on the training data of that outer loop, we need both to select alpha and fit the model. So we split it again into an inner nested cross-validation loop. And then for each fold in that nested loop, and for all possible values that we want to try for the hyperparameter, we train and test all of these models. So if we want to try 10 different values for the hyperparameter alpha, here on each of these folds, we will train and test 10 models. And then we will select the best alpha, the one that gave us the best cross-validation score in here, refit it on the training data of the outer loop, and finally test it on this outer test data. So again, for each of these splits, you see at the bottom, on the bottom line, the set data that has been selected as test data, as left out data in the outer loop. And you see that this one is not used anywhere before for any value of alpha or to fit any model. So we have this outer training data, and we split that again into the several sets of training and validation data. And then once it has been split, for each of these inner smaller training data sets, we fit several models, one for each value of alpha, and evaluate them. So here I will end up with many scores for the different models, average them, pick the best, and once I have picked the best alpha, I fit just one model with that value for alpha on all of this blue data, of the data that was available for training from the outer loop and evaluate it on the test data that I haven't seen at all so far. And like this, I get one score for one model. And I repeat that for different splits as we did before in order to perform cross-validation. So in total, I will fit many models, but for each split in the outer loop, I obtain just one score. And in this whole process, I will end up here with 5 scores because I'm doing 5-fold cross-validation as before. Are there questions about this?
Does everyone understand the outer loop and inner loop distinction? We did talk about it yesterday a bit as well, so hopefully. There are no questions so far.
No? Okay, that's clear for everybody. So can you tell me how many models I will end up fitting when I do this whole thing, where I have 5 folds in the outer loop and 3 in the inner one?
Any guesses? It's not a trick question.
Like one per trait, or
Sorry?
I think one per fold, and then so like 27, 20.
And say I have 10 values for alpha, for example. Sorry, I forgot to say.
Okay, so there are going to be 5 for output. There's going to be 3 inner folds. So that would be what? And there are how many values did you say for alpha?
10, so 10 values for alpha. Okay. The answer is, one of the answers is 150. If you have 10 values for alpha, I guess.
Remember that here in each fold, I do cross-validation. I fit and test all values for 10 models for the 10 different values of alpha. Once I have selected alpha, I pick the best one and refit the model on this whole blue data and then evaluate it. So in each of these folds, in each outer fold, I have 3 inner folds for which I fit and test 10 models, plus 1 here. Once I have picked the best alpha, I refit it on the whole data, and then evaluate it, and then times 5 because I have 5 folds in my outer loop.
Right, so because the subtle point is one more additional model you train after you get the inner folds. So does that make sense? So like
This part again. So if there were 3 folds here. Each of these train tests has 10 alpha values. So those get multiplied. But once you get all that performance, you do additional one more retake operation. There's one extra thing that. So if it was a trick question, then.
But yeah, I think it's clear. I don't know if you heard me, but
great. So the good news is that we don't have to implement this ourselves, although that's one of the exercises, but we won't have time to do it now. And in scikit-learn, we have an estimator called Grid Search CV that does this for us. So here again, you have the links to the reference documentation and its description in the user guide, in the more narrative documentation. And we initialize it with one base estimator, like the ridge regression we have been using from the start, and a grid of possible values for the hyperparameters. And in that case, ridge has only one hyperparameter, which is the alpha. And if we want to try these 3 different values, for example, we give that as a dictionary to this grid search CV object. And once we have initialized it like this, it implements the same estimator API with the fit and predict methods that we talked about before. So we can treat it as any other scikit-learn estimator, as if it was a ridge or a lasso or whatever estimator we want, because it has that fit and predict interface. So then we can feed it, for example, to this Crossvalidate score or cross-validate method, and it abstracts away from us the hyperparameter selection and the inner loop of cross-validation. But when we call fit on this grid search CV object, we give it all this trained data to fit on, and under the hood, it will take care of splitting it, doing an inner loop of cross-validation, selecting alpha, refitting it, and returning us the best estimator fitted on the whole data. So to us, it's like a meta estimator that is able to set its hyperparameters on its own by itself on whatever data we give it. That's the general meta estimator that will work with any model here and any grid of hyperparameter. However, some specific models can do this more efficiently, or they can have a smarter way of selecting their hyperparameters, or they can do it faster. For example, when we fit a ridge regression model, we can get leave one out cross-validation scores essentially for the same computational cost as fitting just one model. Because what takes time is computing an SVD of the design matrix. And once this is done, there's a computational trick that allows us to get leave one out cross-validation scores for a wide range of hyperparameters alpha very quickly. So there is a specific dedicated estimator in scikit-learn called the ridge CV that does this in the smart way rather than in the generic way implemented by grid search CV that is implementing this whole thing in the naive approach you could imagine. Another aspect is that for specific estimators, we may have more information about the best hyperparameter or a reasonable range. For example, in the case of lasso, which is an L1 penalty, it is possible to compute the amount of regularization after which all the coefficients are set exactly to 0. So in our grid, it's useless to explore values for the hyperparameter beyond that threshold, because we know that all the models after that will be exactly 0. So we can build an estimator that samples a grid between 0 and that maximal theoretical value for the hyperparameter. So if we wanted to do it like this by itself, again, we have a dedicated estimator called the lasso CV. Also for estimators that use an iterative solver, when we have a training data set and we need to fit several models indexed by a hyperparameter that is slightly varying, the solutions, if the hyperparameter changes just a little bit, will be close to each other. So we can compute quickly a regularization path. When we start from the most regularized model, we fit it, and then in order to fit a new model with a different hyperparameter, instead of starting from scratch or some random initialization, we initialize it with the solution we had with the previous hyperparameter. So we are already quite close to the optimum, and we can, like this, fit models for several values of the hyperparameter quickly. So the details don't always matter, but if there is one of these dedicated cross-validation estimators for the estimator you are interested in using, for example, if you have decided you want to use ridge and you see that there is a ridge CV, that is the one you should use, because it will either be faster or smarter or both about setting the hyperparameter. If you don't find one, in that case, you can use the grid search CV and initialize it like this with your estimator, and that will work for any estimator that respects the API of scikit-learn estimators. So let's see how we use this grid search CV estimator by looking at the third exercise. Here you see I'm now importing this grid search CV object, also from the model selection module that provides us cross-validate. Generate some data as before. We initialize a model, but here the value we give for alpha doesn't matter because the grid search CV will take care of reinitializing a new model with the different values of alpha that we're giving it. And here I am calling cross-validate on that model. So here that's the same model that I initialized. At this point, I'm not using grid search CV at all. I'm just fitting cross-validating one model, initialized with alpha equals 1 to the power 4, as we did before. So the exercise is to modify that in order to use grid search CV and automatically set the good hyperparameter. So yeah, that's what you need to change this line and replace the model here. That is a simple ridge estimator with a meta. I think we can move on to the solution.
Any questions so far? Anybody has any answers for the scores? If you're stuck somewhere, just raise your hand. I can come and fix on your laptop. All good? Your question?
All the answers.
Do you have answers?
Yeah.
Okay.
All the error scores.
Yeah, sure.
Yeah, like I did the negative mean absolute error, and I had to do like minus 50 to minus 75.
Okay, so it's minus 50 to minus 75 for negative mean squared error?
Negative mean absolute error.
Absolute error, sorry, negative mean absolute error. Anybody else? I think.
Okay, so the way we initialize it, it's actually the very same thing that's on the slide. We initialize the grid search CV with a model and a grid of hyperparameters that we want to try. And then when we fit it, then we can use it as any other estimator, as any other model, as we do here. And for example, use the cross-validate function with it. And when we do that, we see that for each fold in the outer cross-validation loop that is created by cross-validate, the grid search CV is telling us that it's doing its own inner cross-validation loop, splitting the data into 5 folds, fitting models for each of these 3 candidates, which are the 3 potential values I selected for alpha. And then it selects the best alpha and refits it and gives us the scores that it obtained. So if I look at the scores I had with the original alpha that I initialized with the original model I initialized with arbitrary value for alpha, I can see that I am getting R2 scores that are close to 0 because I set a rather large value for alpha. Whereas if I use the grid search CV and choose and pick a better value, I'm getting some better test scores that we can see here. And then, as I said, there's this ridge CV dedicated estimator, which also does some kind of inner cross-validation to select a good hyperparameter, but does it in a better way, so it's faster. And that enables us to give it a bigger grid of hyperparameters. And in this very simple example, we won't see very big difference in the scores, but if we look at the fit time, even with this tiny data, we can see that it's being fit faster, because here it's here is the fit time using the ridge CV, and here is the fit time using the generic grid search CV. Of course, here the data is very small, and we use rather a small grid of hyperparameters. But if we had a more realistic problem, the difference would be even much larger. Is that okay for everybody?
Yes.
Great.
Why are there?
Sorry, Jerome, there's a question. Hold on.
Why are there 5 numbers that came out from research, like 7 numbers in?
There were 5 folds. So there were 5 alpha folds.
Okay, but there's not. It's not. How do I pick what the alpha that is the good alpha?
So Jerome, could you go back to the list of all the scores so we can, I think the question was, how do we pick the best alpha?
And why doesn't it correspond to anything in the alpha?
How do we pick
And
the
how
best
do you
alpha?
correspond, sorry, yeah, how do you correspond your alpha, the selected alpha to the output of your score?
The scores we're seeing here, they
Yeah,
come,
exactly.
they come from the cross-validate function. So this function, we give it a model, which happens to be a grid search, but it doesn't care about what the model is. It just uses its fit and predict interface as for any other model. So the 5 scores we are seeing here are the scores from the outer cross-validation loop of the selected and refitted ridge with the best hyperparameter.
So just wait a second, Jerome. So when you think those scores are the test scores, right? So those are the 5 scores that he's talking about. Go ahead.
The scores we are seeing here are these 5 scores here. So in each inner cross-validation loop, the grid search selects the hyperparameter, then refits the best model on its whole data, and then cross-validates, evaluates, and then it returns one model, the ridge using the best hyperparameter refitted to the whole training data, and then the cross-validate function evaluates that model on the testing data and produces one score. And because the outer cross-validation loop has 5 folds, we end up with 5 scores.
Right. And how do you find the optimal lambda in this way?
So the optimal lambda is not guaranteed to be the same for all of these. So that's really an internal value that is interesting for grid search CV itself, or the ridge CV. But it depends on, it's specific to a particular grid search CV that has been fitted. So if you wanted to inspect that, there are, you can tell cross-validation functions in scikit-learn to return the fitted model, or you can refit one model on the whole data and inspect its inner cross-validation scores and the alpha it happened to select. But these are kind of internals to the grid search CV.
Cool. It's clear. Thanks.
Yeah, for those who are interested, there's this exercise here where basically we have a skeleton for a simplified implementation of that, a very simple implementation of that whole thing with the cross-validation. And you are asked to complete it, and you have the solutions as well. But we don't have time to do this now. So we'll just continue and now talk about dimensionality reduction. if you remember, I said before that when we have many features in X or features that are not linearly independent, we need to somehow constrain the model and make the problem we're trying to solve better posed. And we saw one way of doing it, which was regularization. Another approach is to reduce the number of columns in X so that we have less parameters to choose. Instead of constraining the parameters themselves, we transform our problem so that we have less parameters to choose. And that's called dimensionality reduction. And there are many ways of doing it. So when we do this kind of dimensionality reduction, we add one step in our learning pipeline. Until now, we had the features X. We would fit our grid regression, for example, and output a prediction Y. Now we are adding one step in that transformation. We add a dimensionality reduction step that will transform X and produce a new design matrix with the same number of samples, but a smaller number of columns, and then fit our original estimator on this reduced data. So to motivate this a little bit, I generated some simulated data. Again, with that same simple thing we have been using to generate simulated data sets from the beginning. But this time, we have a lot of noisy columns in X that are not informative. So we have 3 columns, 3 features in our design matrix that have some linear relationship with the target Y that we will want to predict. And then I add a lot of columns that don't carry any information at all. And I add more and more, increasing the dimension of the features and making the learning problem more difficult. And then I can see as I increase the dimension of X, what happens with our training and testing mean squared error. So, as I said, there are only 3 actually informative features. And here on this axis, you see the number of features. So we start from 3, the 3 that are useful. And then I add more and more garbage features that don't contain any information and just increase the dimension of X without adding any information about Y. And we see that as the dimension of X increases, the model has more coefficients that it can choose, and it becomes able to fit the training data set better and better. Sorry, that's the error. So here we're seeing the training error, and this error is decreasing because the model has more coefficients, it becomes more flexible, and is able to fit the training data set. And if we get close or beyond the number of samples that we have in our data set, then in that case, we end up with more columns than rows in the design matrix. So the model is able to fit the training data perfectly, and we get a training error that goes to 0. But of course, it's only fitting noise in the training data, and all that it's learning is not helpful at all and does not generalize to testing data. So although our training error is decreasing, the testing error keeps increasing until it gets very, very bad when the model is completely overfitting the training data. So we will try to fix that with dimensionality reduction. And one of the simplest strategies for reducing the dimension of X is univariate feature selection. We just look at the columns of X one by one and compare them to Y and try to guess if there seems to be some kind of association between that feature and the target we are interested in predicting. So we screen the features one by one. For example, if we're doing regularization, we can compute the correlation between Y and a column of X. And if the correlation is very low, we discard that column. If it's high, that column may be useful to predict y, and we keep it. And you have many different kinds of strategies to decide if there is likely to be an association between that column of x and y, and all of them are all those that are implemented in scikit-learn, and more information is in the scikit-learn user guide. So again, I look at these columns of x one by one, compare them to y, and decide which are the most promising, and I will keep only those. So I look at that first column, compare it to y, I see that they are not very correlated, and I decide to discard it. But when I look at this one, I see that there seems to be some association with y, so I will keep it in my dataset. Like this, I discard some features, I keep some other features, and I end up with a smaller design matrix that has fewer features. And when I fit my model, I have less coefficients to fit, so I have a much easier problem, and I have less variance in my coefficients. And if I do this, so in blue are the same curves we were seeing before, and in orange we see the corresponding curves for a model where I applied this feature screening and I kept the 10 best. So I'm still, of course, in any realistic scenario, I don't know most of the time how many useful features there are, but that's also a hyperparameter that I can set. In this case, I decided to keep 10 features, which is the default in the scikit-learn feature selection. I end up with only 7 garbage features and hopefully the 3 informative ones. And I see that my model is not able to overfit, so the training error remains rather high, but that also prevents the testing error from exploding. And this means that even when I add a lot of features, which was completely derailing the model before, now its performance remains close to the best performance we can hope for, which was what it was getting when it could only see the informative features. And this particular strategy for dimensionality reduction in scikit-learn is implemented by the select k-best class. So the pipeline with dimensionality reduction and then some predictor concretely could look like first the select k-best transformer and then the ridge regression that we were using before. And this introduces a different API that we have in scikit-learn, which is the transformer API. So before we had the estimator, the ridge that has some fit and then predict. And previous steps in a pipeline are called transformers because what they output is not a prediction for y, but a modified version of x that can be fed to subsequent steps. So it looks like this. We initialize that transformer, and here again we could set some hyperparameters. Then we fit it to the training data, and instead of predict, it has a method called transform, to which we feed the features, and it transforms. So in this case, it returns a version of these features with only the selected columns, so with a smaller number of columns. And for convenience, it also has a method called fit transform that does these 2 steps in one go. So we just call fit transform, and it fits itself to x train and y train, and then returns the transformed version, so the dimensionality reduced version of x. That's one less line for us to type, but also it can be faster because in many cases, in order to fit the transformer, it actually ends up computing as a byproduct the transform representation of x, so we might grab it right away instead of having to recompute it. Here you also have links to the user guide that describes this whole feature selection module in scikit-learn, and also the documentation about that fit transform API. Again, when we run this code, what happens is that the transformer is fitted to the training data. So for our regression problem, it computes the correlation of y with each column in X. It remembers the indices of the columns that it chose to select, of the k columns it selected, where k is a hyperparameter that we can choose. And then when we tell it to transform either X-train or X-test, it drops the other columns. So it indexes the X matrix to keep only the selected column, and returns to us a matrix of dimension n rows and samples, which is the same as before, and only k columns. And here is the reference documentation for that particular transformer. Is that clear so far? Okay. So remember that we can only learn or fit anything or choose anything on the training data. And that is also true for the feature selection. In the same way that we cannot fit the coefficients of the ridge on the testing data, we cannot select the best columns on the testing data either. So we have to fit and transform the training data, but then when we need to transform some testing data, we do not refit the transformer. First of all, it wouldn't work at all, because then it would perform a different transformation than the ones that subsequent steps have seen during training. So the new output would be meaningless to the following steps in the pipeline. And also, we cannot fit any of our estimators to the testing data. So we should always take care of respecting that training and testing split for all the steps in our pipeline, and not only the last one. So when we do any kind of pre-processing, feature selection, and so on, we have to do this on the training data only, and not on the whole data set. So if we take our whole data set, do some kind of pre-processing and feature selection to end up with a transform version of X, and then do cross-validation of the estimator on that transform data set, we are overfitting our data set, because we have used the test examples to do the feature selection. So really, we should start from the data set that we haven't transformed at all, split it first. The first thing we do is split training and testing data, and then all the different steps in the pipeline are applied only to the training data, are fitted only on the training data. That could get a bit annoying to implement ourselves every time. So scikit-learn has something called a pipeline that can chain several transformers and a final estimator. And again, once we have created that pipeline, it exposes the estimator API, so it has a fit and predict methods. And to us, it looks like any other scikit-learn estimator, and we can use it as if it was just one model, like the ridge, and feed it to cross-validate, put it in a grid search CV, do whatever we want with it. It abstracts away from us the fact that there are several steps, each of which needs to be fitted in a sequence. So there is also a convenience function called make pipeline, where we just give as parameters. Here we can have as many parameters as we want, and we give the different steps in the pipeline. So here we are creating a simple pipeline with only 2 steps, a feature selection step, and then a ridge regression step. And this thing will return to us a model that is a scikit-learn estimator with a fit and predict method, and that we can use as we used the ridge before, or as any other scikit-learn estimator. And for example, to which we can apply cross-validate. And that's what we are going to do in the 5th exercise. We still make the regression as before, and now we can look at just this code. So I have my X and Y data, and now I start by doing some dimensionality reduction with the feature selection. So I have select k-best transformer that does the dimensionality reduction for me. I initialize it with the criterion I wanted to use in order to select the best column, and then I use it to transform my data set. And like this, I obtain a smaller X. So now X reduced is a transformed version of my design matrix with a smaller number of columns. So I have now X reduced and Y that constitute my data set, and I can obtain scores by using cross-validate with my estimator, but this time using a smaller X, so I should get some better scores, and the same Y. So it should be easy. Can you tell me what is the problem with this snippet of code?
Did everybody hear about X reduce and X means? So if you had 1,000 features, and so the X would have 1,000 features, but when you reduce the dimensionality, you'll have say 100 features. So X reduces the fewer number of features you'll be using to train and test your model. But the question is, what is wrong with this process right now? Yes.
It's using a transform on all the data.
Exactly. So it's going to be all the data, as in all the samples, not the features. So it's always important to remember when you say data, are we meaning features or samples?
Yeah, so the answer was basically you're transforming the entire training or entire data set using all the examples from the data set.
Exactly. So the error is here is that I am fitting that select k-best feature selector on the whole data, whereas I should do that only on the training data. If I didn't have the pipeline from scikit-learn, that would prevent me from using cross-validate, because I would need to dig into each k-fold step myself and then fit the select k-best, get the transform data and fit that to the ridge and remember the ridge. But luckily, we have the pipeline class from scikit-learn that allows us to package together both of these steps and treat them as a single estimator so that it works with the cross-validate function. So for now, if I run it like this, I only get the results I would get by overfitting the feature selection. So I see these are two scores. And what I would like you to do is now implement it correctly by using this make pipeline function in the way that it's shown on the slide to package together the feature selection and the ridge regression, and then cross-validate that meta estimator, that pipeline, and obtain the correct cross-validation scores. And then we will be able to compare them and see if overfitting the feature selection made a big difference. And that is the last exercise we have today. So try to do it, and then I will leave you alone with the exercises.
Is everybody clear on what's supposed to be done?
And here also, don't hesitate to look at the scikit-learn documentation for the
Tutorials with the fMRI data, is that something they can do on their own later?
yeah, sure. We're not gonna do them here.
Yeah. It's the extension of the same, I think, tutorial that we did yesterday, I believe. Just
I think
with
so.
this,
I
yesterday
think
we did
so.
only one train and test split, but now that you guys are more familiar with how to do cross-validation and pipelining, you could basically apply these techniques to do the whole autism site prediction problem if you guys were there yesterday. If not, you can
Yeah.
also take a look at that example from yesterday's slides and the GitHub repository. The links are all on the website.
So yeah, it's a bit of applying all the things we have seen, but just on fMRI data instead of simulated data. So we have a pipeline to chain scaling and connectivity, extracting connectivity features, and then doing a logistic regression for a classification. And we are using make pipeline. And I don't know if this one doesn't use grid search CV, but it's basically an illustration of what we have been doing, but on fMRI data. And I don't remember what are the questions.
Yeah. Anybody got the box plot for the other? Yeah. What was the mean performance?
You want me to read it off?
Sure.
What's yeah? So do you see a big difference between the two?
Yeah. They are seeing a big difference between the whole data versus using trained data for your pipeline building.
Okay, so it's the same thing as in the slide. I can initialize my pipeline by giving it the different steps. So first the selection and then the ridge. And once I do that, I get this model that has the scikit-learn estimator API that can treat as any other model, and in particular feed to cross-validate and get the cross-validation scores. And if I run this, here are the scores I get. So these are the R2 scores I had when I first transformed the whole data and then did the cross-validation. And they seem very good, but if I do the cross-validation correctly and fit my whole pipeline only on the training data, I see that I get much worse scores.
This is also referred to as double dipping sometimes. So talk about it yesterday.
Then I'll talk very briefly about another way of doing dimensionality reduction. We have seen the feature screening one that is looking at columns one by one. It's probably the easiest to understand. Another one that's used a lot in neuroimaging is linear decomposition. Because sometimes we can reduce the number of features, but the ones we can drop may not be exactly aligned with one of the dimensions of our feature space. So if I look in this case at some data, maybe I see that my data varies a lot in one direction and not so much in another one, and I could drop that feature and keep with this one and still keep most of the variance in my data, but sometimes it doesn't line up as neatly. And in this data set, if I were to drop either of these features, I would lose a lot of information, a lot of variance in the data, simply because there is a dimension where there is not much variance in the data and I could drop, but it's not aligned with the basis of my feature space. So I need to identify the directions in which the data varies a lot and that I want to keep so that I can drop the other dimensions. So I need to reparameterize my feature space in order to be able to reduce the number of dimensions while keeping as much information as possible. So linear decompositions allow us to find a new, better basis in which to represent this data so that we can reduce its dimension while keeping a lot of information. So instead of just dropping some columns of X as we did before, we will find a decomposition of our feature matrix X so that it can be well approximated as a linear mixture of a few basis vectors. And then the coordinates in this new basis will be the transform features. So here I still have my design matrix X that has way too many columns, and that makes it difficult to fit my model as before. And instead of using the whole X, I will build a low rank approximation of it. So I will try to approximate it as a product of two much smaller matrices. So again, instead of having all of X, I try to approximate it by multiplying together two small matrices. And then I will end up with a version of X of a much smaller dimension. So I'm trying to find a few vectors in the same space as the columns of X that I'm trying to use in which I will represent Y by computing its coordinates in this base. But instead of having the same number as in X, I just have a few. So I'm trying to approximate X as a linear mixture of just a few well-chosen columns. And to estimate that approximation, to say if this is a good reconstruction of X or not, one criterion that is easy to work with is, again, the sum of squared errors. So there are many variants of that idea that use the sum of squared errors and minimize it while adding some constraints or some penalties on these two factors. And once I have computed this factorization, I can, instead of X, use this reduced dimension representation. And then when I fit my linear regression, I have fewer columns in my new design matrix, fewer coefficients to choose, and I'm working with an easier problem. And if I was able to build a good low-rank approximation of X, I am still capturing most of the information that was in my design matrix in this reduced dimension W. So I should still be able to approximate Y quite well. And then to represent when I am testing the model and I get some feature vector that has that dimension of the original feature space, I can just regress it on the other factor here to get the coordinates in that new space that give me a good approximation of my feature vector, and use that coordinates as features in order to build my prediction. So I take my feature vector for my test sample, project it on the smaller family that I selected to get its coordinates, and then map that to a prediction through the coefficients that I learned when I fitted my model in the reduced dimension space. Concretely, one way of doing this kind of decomposition is principal component analysis. Yeah, is there a question? No?
No, very good.
Which consists in finding one by one the directions that explain most of the most variance in X. So if this is my features, in this case, I'm showing only two dimensions in X. I find the directions that capture most of the variance of my data. So the first one would be this one, and then the second one would be this one that is orthogonal. And this is done easily by computing a singular value decomposition of X. So I minimize the squared error of the reconstruction as I showed before. And my factorization, I write it as the products of U and V. So here, this would be U, some matrix S, and this would be the V, where each of their columns are of norm 1 and orthogonal, and the S are the singular values, so they give the scale, the scaling factors for my data in that dimension. So maybe it will be simpler with an illustration. I have here my design matrix X with n samples and p features to start with, and I try to build an low-rank approximation of it as a product of these matrices U and V. And I do that iteratively by first trying to find the pair of normalized vectors U1 and V1, that when I compute their outer product, it will give me the best possible approximation of X in terms of the Frobenius norm. Of course, here I'm just I just have two vectors, so I'm building an approximation of rank 1. So as you can see, it's not a very good approximation. But then once I have done that, I try to look for another pair that I can add that will improve as much as possible my approximation. So at first I have only 0.5 explained variance, and then I look for the next pair that I can add, and my approximation improves, and so on. And each time the rank of this product is increasing, and my approximation is getting better. And if I keep doing this until I have as many terms as the rank of X, so as the smallest of N and P, I will get a perfect reconstruction of X. And then what we do is that when we want to do dimensionality reduction, we compute these terms and keep only the K first. So I would say that if I want two-dimensional approximation, if I want to reduce my dimension to 2, then I keep only the first two terms in the decomposition, and I will have only two coefficients to fit in my linear model afterwards. And there are many other decomposition methods that use the same sum of squared errors, as I said, but add different penalties or constraints. So you have maybe heard before the terms dictionary learning, non-negative matrix factorization is something similar, but with the constraints that each of the factors has to be positive. K-means clustering also minimizes the sum of squared errors, but here instead of having continuous numbers, I must have discrete assignments to clusters, and so on. And all of these are unsupervised dimensionality reduction methods, because I'm looking only at X when I choose the transformation, but there are also other methods that take Y into account in order to choose a reduced dimension that captures well the information in X, but that keeps the information in X that is useful to predict Y. Also, I just want to point out that this kind of doing a PCA and truncating it and then fitting a linear regression, it's not that far from doing a ridge regression, as we have been doing from the start. Basically, they both compute the SVD, and then the ridge, due to the regularization that it adds, it shrinks the coordinates of y in the basis of the column space of x that we computed with the SVD. Whereas when we truncate the PCA, instead of shrinking the coefficients, the coordinates of y, it simply keeps the first k and discards the others. So although their implementation is different, and in one case we see it as two steps of dimensionality reduction, then linear regression, and the other is just one ridge regression, they are not that far apart. And now I'll just, yeah, sorry, are there any questions?
All good?
Yeah, you're
Great.
good.
So I'll just conclude with a small summary of the errors that we want to avoid when evaluating the performance of machine learning models. And the important thing to remember is that our cross-validation experiments are there to simulate what will happen when we deploy the model in real life in order to help us to figure out what will be its performance. So if we are training a machine learning model on some research data set and then we want to deploy it in production or in a hospital and apply it to new unseen examples for which we actually want some useful predictions, we want a way to simulate that process in order to have an estimation of how well it will perform on these unseen examples. And in order to simulate that event, we split the data and leave out some of the examples that will, in this simulated scenario, be the patients we will see in the hospital. That's our test set, and the training set corresponds to the data set we have that is available to us for designing and fitting our machine learning system. So if we keep in mind that this split of training and testing is there to simulate deployment in a new environment where it will see some samples that were never available to us, that helps us to detect some problems in the way we validate the model that violate that scenario and make our simulations unrealistic. For example, if we do the dimensionality reduction or the feature selection, as we said, we have our research data set. We can reduce the dimension, fit any model we want on it. When we send our model to the hospital, it will see some new examples that, of course, we could never have used to select the most informative features. So if we do the feature selection using our whole data set and then cross-validate only the subsequent steps, that's not a very realistic simulation of the deployment of a model, because we have done something that in real life we could never do. In the same way, if we use all the data to do the hyperparameter selection, that's also unrealistic, because the patients that we will see in the future in the hospital, we couldn't bring them in to try our model on their data, to try different models on their data, and select the one with the best hyperparameter. So in order to make that simulation realistic, we have to figure out a way to select just one single model and its hyperparameters and fit it without touching at all the final test data that we will use to evaluate its performance. So keeping in mind that our cross-validation experiments are there to mimic the deployment of the model can help us falling into these traps that lead us to overfitting either some steps in a pipeline or the model or hyperparameter selection. And here is an example. If I'm fitting some data to, if I'm fitting some models to predict data in a time series, say predict the weather or something that will happen tomorrow. Here I have all the points. So this here is time. I have all the points in my data set. I can split it in different ways in order to do my cross-validation. So I could split it like this, or I could randomly choose in the data set which points go into the training data and which go in the testing data after shuffling them. So in blue, I have the train data, and in orange, I have the test data. I will fit on the blue points and then evaluate my model on the orange point. So can you tell me which of these ways of splitting the data will be the most challenging for the model and which is the most realistic?
Who thinks is the top one is more realistic? Okay.
We have 3 people for the top one to be more realistic.
Right, because if then in real life, I take my historic data up to 2022 and fit my model on it, and then I want to deploy it, and it will have to make some predictions about 2023. Of course, I couldn't mix in some data points from 2023 in my training data in order to fit the model, because they haven't happened yet. So if I shuffle the time points between before splitting my data set into train and test data, I am making a different task that is much easier, because now the model just has to interpolate between the time points instead of making a forecast. So there's not one way of doing cross-validation that is good in all scenarios. Every time we set up some cross-validation, we have to stop and think about what model we are training and for what we will do with it later, and what would it look like to deploy that model and start using it once we are finished building our machine learning system. And then we have to set up some cross-validation experiment that gives us a realistic simulation of that scenario. So we have to choose the appropriate cross-validation iterator, and in scikit-learn we have several. So we have the k-fold we have been using, but also we can have stratified k-fold that tries to keep the same proportion of different classes in each of the testing set. An important one is group k-fold. When we want to group the data, for example, if we have several data points for each participant, they have come several times to the hospital and been scanned several times or something like that. Again, if we mix them, if one participant has some of their data in the training set and some of their data in the testing set, that's probably not realistic, because we want to see how the model will generalize to some new patients who will come to the hospital in the future and whom we haven't seen at all. So we have to take care of putting, if we have put some of the data for one patient in the training set, not evaluating the model on more data from that same patient. That's what group k-fold helps us to do. And another example is, as I said, the time series split, where we make sure that we don't put any time points from the future into our training data. Another, yeah.
Actually, you can finish this. I will. Well, so there was another question before you, I guess, move on to the next part.
Yeah.
The question was the dimensionality reduction that you talked about. Is it specific for regression problems, or are there also applied to the classification problems? And are there better ways to do reduction for the classification problems?
No, it also applies to classification problem, because the linear decomposition that I described, it only looks at the design matrix anyway. So it's just trying to find a simpler representation of the input information while keeping most of its variance. And then once we have that simpler information, simpler representation, we start looking at Y and fitting a model that regresses Y on the data or does classification.
Cool. Yeah, I will write that down in the Discord. So yeah, it's fine.
Sorry?
No, that's yeah. The question was on Discord, so I will write it there. But you can continue.
Okay. Then another mistake that we see often is that we cannot forget that when we do cross-validation, the training sets overlap. So when I do the split like this, in the first and second fold, some of the data is in both training sets, because otherwise we would waste a lot of data. So the scores I get for each of these folds are not independent. So whenever you read that we have done 20 or 100 fold shuffle split cross validation, and then we get 100 points, and we do some statistical tests to claim that the score is significantly above some value. That doesn't work, because it violates one of the hypotheses of the statistical test, which is that the samples are independent. So remember that when you see a claim about the significance of some cross-validation score, most likely it's not justified. And just summarizing everything, we have to avoid overfitting the hyperparameters. We can't use test data to select the best model or the best hyperparameter. And to avoid this, we can use the grid search CV from scikit-learn or any of the CV estimators. We have to avoid fitting part of our pipeline on the whole data set. So we cannot use testing data for pre-processing, rescaling, feature selection, or anything like that. And to easily avoid making that mistake, we put all of our steps in a scikit-learn pipeline. We have to remember to build realistic cross-validation experiments that mimic the deployment of a model in production. And for that, we have to think, what does this scenario look like, and choose the appropriate cross-validation iterator, as in the time series example. We have to remember that our cross-validation scores are not independent. And we also should avoid over-interpreting good cross-validation scores that we have obtained on a single data set if we plan to deploy the model to, for example, a different hospital, or if there might be some dataset shift between what we have been using to train and validate the model and what it will actually see in production. And that's often a challenge, because, for example, the scanner we have used to collect our research data is not the same that the one that's used in the hospital, or a researcher has been collecting answers to a questionnaire, but they don't do it in exactly the same way as the practitioner who will do it in the hospital, and so on. So there might be some shifts that we are not aware of, because of course, when we split randomly our dataset into training and testing data, the training and testing data come exactly from the same distribution, which is one of the hypotheses of most machine learning methods, supervised learning methods. And if we deploy it against data that comes from a different distribution, that hypothesis might not hold anymore. So even if we had good cross-validation scores on one dataset, we might be disappointed by the performance of our model once we start using it. So it's good to try to come up with other experiments we can do, trying it on a different dataset and so on, to get a better guess of what will be its actual performance. And that's all I wanted to present today. So thank you all for listening to me. And do you have any questions?
Any questions for the talk, or in general for your own research? Any confusions you have for this machine learning? Cool, then that's perfect timing because we're all hungry. Let's just
Great.
thank Jérôme again.
Thank you.